Another kind of IP address is Internet Protocol version 6, or IPv6. So recall, the purpose of an IPv4 address originally was to allow you to stitch multiple different networks together. So provide this globally unique identifier which would be usable across many different networks. But so one of the problems that's emerged, especially recently, is that the IPv4 address space has only 32 bits. So there are only 2 to the 32 IPv4 addresses, or approximately 4 billion. This seemed tremendous at the time, back when the internet was 60 nodes, but today it's actually a limiting factor. Generally, for a variety of reasons, in any kind of numbering scheme like this, you look at telephone numbers, etc., or utilization never going to be 100%. So in fact, utilization of the IPv4 address space is around 35%, where only 35% of the IPv4 addresses are active at any time. And the challenge here is that if you don't have an IPv4 address, then there isn't a way to communicate with IPv4. You need an IPv4 address to have IPv4 communication. The other side needs an address to send an IP packet to. And so realizing there was possibly this shortness, this scarcity of IPv4 addresses, plus a couple of sort of crufty things that people saw in IPv4, work started on a new version of the Internet Protocol in 1994 called IPv6, or Internet Protocol version 6. The basic protocol for IPv6 was published in 1998 in RFC 2460. And then there was a lull for a good while. Well, still, I mean, you think 1998, this is, just before a couple, 2 years, 1 year before the first .com boom and bubble. The internet's taking off, but by no means is the IPv4 address space close to exhaustion. So there was a lull of work, but there was an increased interest then in around the 2003-2006 timeframe. People started to get a better handle as to what were the challenges in IPv4 networks, what's important, what's not, how should we use IPv6 addresses based on current network utilization and designs. And so today there's actually a hard push within the IETF as well as several governments to adopt IPv6. You can imagine, especially countries or regions where growth of connectivity is very large, say in China, the scarcity of IPv4 addresses is perhaps a greater concern. And so there's a big push today to get IPv6 deployed and in use in the internet as a whole. So what does an IPv6 address look like? So IPv6, rather than being limited to 2 to the 32, has 128 bits of address. So this is absolutely enormous, 2 to the 128, so approximately 3.4 times 10 to the 38 addresses. This means that you could have 21 IPv6 addresses per square inch of the world's surface. So at least with the idea that an IPv6 address is going to name a device, as long as we have fewer than 21 devices per square inch, we'll be able to hold up at least on the Earth. Of course, it might well be that these addresses are used for more than that, but still. And generally speaking, an IPv6 address is separated into two parts. There's the subnet prefix, which is of, say, length n, and the interface ID within that subnet, 128 minus n bits long. So think of this similar to a CIDR address or a CIDR class, where you have the net mask describing what's the network identifier and then the set of nodes within that. Now, you don't really want to write 128-bit addresses as 16 little octets. Plus, often they have big regions of zeros and repetitions, and so IPv6 addresses are written differently than IPv4, where IPv4 is written as a simple series of period delimited integer values. IPv6 addresses are written in hexadecimal as 8 blocks of 16 bits. So here's 16 bits. This is 2 hexadecimal. There's 2 zeros, 0, 1. And here's the second. There's a leading 0 here, which has been elided, 0470, 806D, 1::9. If you have a long run of zeros, you can omit a single one of those with : : So what this is really saying is, here's our first block, here's our second block, here's our third block, here's our fourth block, this is our eighth block. The fifth, sixth, and seventh are all equal to 0. Right, so if I were to write this address out fully, you'd see
2001:806D:1:0:0:0:0:9.
And there's a prefix line here of 64 saying that the subnet is 64. The last 64 bits denote the actual address of the node, which in this case is this. You can also, if you want to use an IPv6 address in HTTP in a URL, say in your web browser, you can do it by putting it into brackets. So this says to contact this node, this IPv6 address, port 80 in the URL. And it's also possible, if you want, to write the low 32 bits like IPv4 as an IPv4 address. This because that's one way to make IPv4 addresses addressable from IPv6, is you have a leading 96 bits denoting this is an IPv4 address, and then you stick the IPv4 address at the end. So we have these enormous 128-bit addresses which allow us to add many more devices to the internet. So how do you assign them? Currently, so you look at IPv4, you have IANA and ICANN and RIRs handing out /8s, and the RIRs take the /8s, the blocks of 16 million addresses, and distribute then to companies or organizations or whatever as asked. And so it turns out that actually how you assign IPv6 addresses has gone through a couple of iterations as people have gained better experience and refinement. So for example, one of the first RFCs on this, RFC 3177, said that generally you want to give people a /48. Sometimes you want to give them a /64. Very, very rarely give them a /128. Right? So this would be that we have 48 bits identifying the network, 80 bits for which then they can use the interface ID. Sometimes we get 64, where then 64 denotes the interface ID. And occasionally you'd have just essentially the single 128-bit, so you're giving just one address to somebody. RFC 6177, after many years of experience, said, this isn't a great idea. So you want to give out at least /64s, which I mean, you don't want the 64 to be any higher than that. You do not want to be giving out 128. So give out 64s, or maybe 60s even, or 56s, as needed. The observation is that 48 is a lot, much more than almost anyone needs. And there are lots of cases where people needed more than 164, and so you can allocate it. And then kind of like how IPv4, when you go to a regional internet registry and you ask them for a block of addresses, they're going to ask you how many, and they're going to make a decision as to whether or not, if you ask, say, for a /23, they're going to decide whether you really need that number of addresses. In this case, 512 addresses. And in the same way, today, RIRs can decide on the allocation size. So do you get a 64, do you get a 60, do you get a 56, etc. Great, we have this way of distributing distributing IPv6 addresses. So how do we actually get an IPv6 address? So if you look at something like DHCP, you basically need to ask for an IPv4 address, and it's independent of anything else. But the IPv6 address space is so much larger. It might be you can do something a lot simpler and just simplify the configuration devices. That's exactly what it does. So it turns out that if you have a /64 subnet, that is, your organization has a /64, so 64-bit subnet network identifier, you can then automatically generate your own IPv6 address just from this subnet identifier. So it turns out that Ethernet cards, this is assuming they're using Ethernet, which is basically what almost everybody uses today. Ethernet devices have 48-bit. They have a 48-bit unique identifier. It's their layer 2 address identifies the actual device. It's specified at manufacturing. It's baked into the card. Often you can reprogram it, but it's baked into the card. And so the Ethernet address looks something like this, where there's a manufacturer code, right, saying, oh, this was made, say, by Apple, or was made by Dell, or was made by Oracle, or was made by HP, or Cisco. So these codes are what an organization gives out, and then when an organization, needs a code, it can then use the lower 24 bits to basically produce 16 million devices with that code. If it's a new code, it gets a new code. And this 0 here is to denote just for unicast MAC address. G is 0, and then there's a unicast MAC address. And so what you do is you take this Ethernet address, this 48-bit Ethernet unique identifier, and you perform a transformation. You basically add some ones in the middle. You flip the 0, or you flip the 0, and you add FFFE, so FFFE into the middle, and you can then get a 64-bit identifier. So now if I know my organization's 64-bit subnet ID, let's just say it's X, and I know my Ethernet address for my hardware card, which is, say, Y, I can then take Y, put it through this function, and now my IPv6 address is just those first 64 bits with then these latter 64 bits. And so this is specified in RFC 4291. And so here's an example of how you have what is a large address space, and that the size of the address space being 128 bits actually gives you a great deal of flexibility in terms of assigning addresses. So for example, one thing you could point out is every single Ethernet device has these same 2 bytes in it. You're not going to reuse them. So in some ways that's flexible, because it's nice if we want to do something besides Ethernet. We know as long as we don't match these bits, then we can generate an IPv6 address which will not collide with the Ethernet device. But essentially just that tremendous plenitude of addresses gives us a bunch of flexibility and can simplify management, can simplify configuration. So in that way, IPv6 is really nice.